If you were given an equilateral triangle, or what we'll call a regular triangle, with sides of 8, could you find the area? Why don't you pause the video for a minute and then come back and see if you can figure out what the area is. Okay, well, maybe you would have drawn an altitude. And when you did so, it would bisect this 60-degree angle at the top, because an equilateral triangle is an isosceles triangle, and we proved many times in the first semester that the altitude to the base bisects the vertex angle. So that is a 30-degree angle, which means this remaining angle is 60, although we already knew that all the angles were 60. So we have a 30, 60, 90 triangle on the right side. If the hypotenuse is 8, then half of the base, or the half of the other side where the altitude meets, will be 4, and the altitude will be 4 root 3. So finding the area is as simple as taking 1/2 the base times the height, which simplifies to 16 root 3. In this section, we're going to find the area formula for equilateral triangles. We're also going to find a formula for all regular polygons. So take good notes. You're going to have some vocabulary terms you'll need to know. I want you to pause often. You're going to have some additions to your formula sheet and some tutorials at the end. Okay, Ramblers, thanks for watching. All right, when we start to look at the area of regular polygons, we're going to start with a regular triangle, because like the triangle in our example, it will be really handy to know the area, or to be able to determine the area simply if all we knew was the length of a side. So let's take a look at a regular triangle. You recall that a regular triangle has 3 congruent sides and 3 congruent angles. Now if I draw an altitude, that will turn this into a regular triangle into two 30, 60, 90 triangles. Now, all year or all semester, we have said that one of the sides was 2A. Well, I'm going to rename it for the purpose of this example, and we're going to say that each side of the triangle, of the regular triangle, is S. Now, when I draw the altitude to the opposite side, that divides the opposite side, BC, into 2 congruent segments. So what had been S is now going to be S over 2. Since that is opposite this bisected 60-degree angle, so since S over 2 is opposite the 30-degree angle, the side opposite the 60-degree angle will be S root 3 over 2. All right, that gives us all the components we need to determine a shortcut formula for the area of a regular triangle. Let's take a look at it. We start off with our basic formula for any triangle, 1/2 base times height. In this particular example, that will be 1/2 BC times AD, because I'm calling BC my base since AD is my altitude. So I know that BC is S, because that's what we've called the length of a side in this particular example. And the height of the altitude, or the height of the triangle, was S over 2 root 3. If I simplify that, it becomes 1/4 S squared root 3, or even better, S squared root 3 over 4. I want you to put this in your notes as a very handy formula for the area of a regular triangle when we know only one side. Okay, let's move on now to looking at some of the vocabulary of other regular polygons. Okay, now when we begin to talk about some of the vocabulary in regular polygons, it's a good idea to remind ourselves of some of the regular polygons we've seen this year. In Chapter 5, we talked a lot about quadrilaterals. Some of the quadrilaterals we looked at were squares and rhombuses. Now, I mentioned that a rhombus is not a regular polygon because it doesn't have congruent angles. A square, however, was. So these would be regular polygons, or I should say a square is a regular polygon. It's a regular quadrilateral. All right, now let's take a look then at what a regular hexagon might look like. 6 congruent sides, 6 congruent angles. You'll remember from your angle measure formulas in Chapter 7 that we can find the measure of each of these interior angles by multiplying n minus 2 times 180 over n. Okay, let's take a look at a regular pentagon. Regular pentagon is going to have 5 congruent sides, 5 congruent angles. Now, if we increase we can increase the size of a regular pentagon or a regular hexagon, and no matter what, all the sides will stay congruent, all the angles will be congruent. The ratio between the sides will always be 1 to 1. All right, now let's get into two important terms when talking about a regular polygon, that being a polygon's apothem and the polygon's radius. Let's talk about the apothem first. An apothem is a segment drawn from the center of a regular polygon and only a regular polygon. Non-regular polygons do not have apothems, but it's drawn from the center to the midpoint of the opposite side. So that's the definition of a polygon, and you'll want to have this memorized, or certainly in your notes. A segment drawn from the center of a regular polygon to the midpoint of any side. All right, it's going to be perpendicular to the side. That's one of the important properties. So in other words, QPO is going to be a right angle. It's going to bisect the side. So NP and PO are going to be congruent because P is a midpoint. All apothems of a polygon are congruent. So if I drew the apothem from Q to OG or from Q to XG, those would all be congruent, just like radii of a circle are all congruent. And finally, it would be the radius of an inscribed circle. So if I were to inscribe a circle inside this hexagon, all of the sides would be tangent to the circle, and the apothem here would be its radius. Okay, now let's look at the other really important line in a circle, which is the polygon's radius. Okay, so when we look at the definition of a radius, it's a segment joining the center of a regular polygon to any vertex. And once again, it has to be a regular polygon. So this radius is going to bisect this angle here at O. So angle POG is bisected, as would any other of the radii drawn from Q to the vertices. They always bisect the vertex angle. All radii of a polygon are congruent, just as all radii of a circle are congruent. And the radius of the polygon is also the radius of the circumscribed circle. So the apothem is the radius of the inscribed circle. The radius is the radius of the circumscribed circle. Okay, make sure that you have all of these properties of a radius in your notes, along with all the properties of the apothem. If you haven't, stop the video, rewind, and make sure you have all those in your notes. Okay, let's take a look a little bit at how we're going to find the area of a regular polygon using this apothem. So as we conclude the new material of this video, we need to bring back one of the regular polygons in order to explain where this new formula that I'm going to give you is coming from. And I could have used a regular pentagon or a regular hexagon or a regular quad, but since they do so much work in this chapter with hexagons, I decided to use a hexagon for my sketch. Okay, but again, it'll apply to any regular polygon. So here's how it works. The formula is that the area of a regular polygon is 1/2 the apothem times the perimeter of the polygon. 1/2 apothem times perimeter. Pause and make sure that's in your notes. Now let's explain where that came from. Well, if I were to draw the radii to every vertex, you'd notice that this created some isosceles triangles. All of these radii are congruent, and so these would all be legs of isosceles triangles. And if I wanted to find the area of each of these isosceles triangles, I could drop an altitude. Now hopefully you recognize that these altitudes are the apothems. So the way I'm going to determine the area of the entire polygon is by figuring the area of each of these isosceles triangles. And that's going to be, for each one of them, 1/2 the base times the height, plus 1/2 the base times the height, plus 1/2 the base times the height. And what you'll notice is I can factor out of that a 1/2 and the measure of the apothem. So that's how I get the 1/2 the apothem. And what I would be left with was the sum of all the bases. And all of these bases are going to make up the perimeter of the polygon. So that's what gives us the formula for the area of a regular polygon. Okay, Ramblers, a couple tutorials for you to help you through the exercises, but thanks for watching. Okay, number 19 on page 535 brings up a lot of the techniques that you need to use in this chapter when solving problems involving an apothem and regular polygons. So they start by telling us the span equals 30. Well, the first question is, what's a span? And the span is going to be the distance across a regular polygon. So not from vertex to vertex, because that would be the diameter, but from one side to an opposite side is the span. Now, that's only going to be in even-sided polygons, and you can think about why. But the term doesn't come up that much, but here it is. So if the span is 30, that means the apothem is going to be from the center to a side. That's going to be 15. And the way to solve these problems is by drawing a radius also, so that you create a right triangle where one side is the apothem, one side is the radius, and one side is half of one of the polygon's sides. So I'm going to draw one of those right triangles down here, where here's my apothem, here's my radius, and then this is 1/2 of a side. Okay, let's go through and try and solve this. If we know that the span is 30, the apothem is going to be 15, and that's a right angle. We also know that the radius bisects the side, and in a hexagon, the radius bisects an angle. And in a hexagon, the angles equal 180 times n minus 2 over n, which is 120. If I bisect one of these 120-degree angles, then I'm going to have a 60-degree angle down there, which gives me a 30, 60, 90 triangle. So if I'm going to find the area of the hexagon, I remember that area equals 1/2 the apothem times the perimeter. And I'll reemphasize, I think it's a good idea to write out the components of your formula so that you can just plug them in as you find them. So I already know the 1/2. They've pretty much given me that the apothem is 15, so all I need to find is the perimeter. So in other words, I need to find this side of the right triangle I've made. Well, if the apothem is 15 and that's opposite the 60-degree angle, then the side opposite the 30-degree angle will be 5√3. So that's going to be half of a side. So if I multiply that by 2, I'll get 10√3. And if I multiply it by 6, I'll get the perimeter. So the perimeter will be 6 times 10√3. And if I multiply all that out, I should get the total area, which will be 450√3. Okay, let's take a look at part B of this problem. Here they ask us to find the span of a regular hexagon if the area is 32√3. Well, I'm going to set 32√3 equal to the area formula we have, 1/2 apothem times perimeter. I'm then going to draw the triangle formed by the apothem, half of a side, and the radius that you work with a lot in these kind of problems. So here's my apothem on the left. My radius is the hypotenuse of the triangle, and then the last side is the 1/2 of the base. So you'll recall that in a hexagon anyway, as this question deals with, the radius was equal to a side. So I'm going to call the radius S. Don't confuse that with span. I'm calling that S. Half of the base will be S over 2, and that makes the apothem S√3 over 2. Now I'm going to set my problem up again. 32 root 3 equal to this formula, but now I'm substituting my values for the apothem so that my apothem and perimeter are all in terms of one variable, the side. And then for perimeter, I'll put in 6 times s. Alright, let's try and clean this up a bit. Okay, it's not a lot prettier, but 32 root 3 equals 6s squared root 3 over 4. Let's cancel out the root 3's, because that's easy. We can multiply both sides by 4, divide both sides by 6, and we'll get s squared equals 64 over 3. If I take the square root of both sides, I get 8 root 3 over 3 is equal to the side. Not the span, but the side. So how do I find the apothem so that I can double it to get the span? Well, you'll recall that the apothem equals s root 3 over 2. So substituting this value in for s, I can see that the apothem equals a very complicated complex fraction here, but it simplifies to be something not so bad, because the root 3's on top will cancel with the root 3 in the denominator, and we're left with just 8 over 2, which of course is 4. Now, the span has to be double that, so if I can squeeze it in, the span is going to equal 2 times 4, or 8. Wow, that was a big problem. Let's take a look at the last part of it. Okay, part C asks for the formula for the area of a regular hexagon with a given span of s. So we're going to take our area formula and we're going to rewrite it in terms of span. So of course we start out with 1/2 apothem times perimeter. Now the trick is going to be to restate apothem in terms of span and perimeter in terms of span. And to do that, let's go back to our triangle that involved the apothem. Now, you'll recall from the diagram in the book, or from the first slide in this tutorial, that this apothem is going to equal the span over 2. Now, we had represented the apothem as equaling this root 3 times this side. Well, this side was the side over 2, and the apothem equaled the side root 3 over 2. But now we're saying that in terms of the span, the apothem equals span over 2, and so that equals the side root 3 over 2. So let's solve for what this side would be in terms of the span. So if I simplify, the 2's will cancel out, and I will get the side equaling the span over root 3, which, if restated, means that the side equals span root 3 over 3. Okay, so let's go back to our original formula for area. Area equals 1/2 apothem, which we now call span over 2, times the perimeter. And the perimeter will be the 6 times the side, and our side is now being expressed as span root 3 over 3. Alright, let's simplify all this and see what we get. We get an area formula. I'll put it up here in the corner. Area equals span squared root 3 over 2. Why is that? Well, I have span being multiplied by a span, so that gives me span squared. The root 3 doesn't go anywhere, but this 6 is reduced by 2 times 2 times 3. So 6 divided by 12 is why I get a 2 in the denominator. So it's a fancy formula where you could either use area equals 1/2 apothem times perimeter, or it equals the span squared root 3 over 2. It's up to you, ramblers. I'm not sure it's worth it, but it was kind of interesting to see how to get through that problem. The trick was to put all of the other components of the formula in terms of span, and then simplify. Okay, Ramblers, thanks for watching. All right, for 17a, I'm going to use kind of a popular technique that we'll use, and that is going to be that the shaded area that we're looking for is going to equal, I can't find it directly, but I can find it by finding the area of the square and subtracting the area of the triangle. Well, the square, of course, is going to be 6 squared, and then the triangle is going to be 6 squared root 3 over 4. And if I simplify that, I'm going to get 36 minus 9 root 3. That's a really useful technique. When you can't find a shape like the one they're asking for, try subtracting shapes from other formulas that you know. All right, now let's take a look at part B. Part B, you'd think we would take the triangle away from the hexagon. And while that does work, a quicker way is just to do the shaded area is 3 times the area of the shaded triangles. That actually works out to be much quicker. Well, how do we find that? Well, I know that this is a regular hexagon, so all the sides are 6. If I drop an altitude to the base of that regular of that isosceles triangle, one of the shaded ones, I know that it would break this up into 2 triangles. I know that the vertex angle of each of these shaded triangles is 120. So that, when I bisect it, I'm going to make a 60, 30, 90 triangle. So the side opposite the 30-degree angle down here is going to be 3. So, and of course the base will be this side, and that's going to be 6 root 3. If I solve for the third side of that 60, 30, 90 triangle and double it. Okay, so my final area will be 3 times 1/2 the base, 6 root 3, times that height, which we said was 3. If I simplify that, I get 27 root 3. In part C, I'm going to find the shaded region kind of directly. By looking at this 30, 60, 90 triangle from part B, that's the same triangle that's not shaded in part C. And I can see that I just determined that the length of these longer sides of the rectangle are 6 root 3. So I'm just going to find the area of the shaded region directly. It's going to equal 6 root 3 times 6, which will give us 36 root 3. All right, Ramblers, these are some tough problems in this section, but what's important is that you're using 2 techniques. Sometimes we will subtract areas we can find from other areas we can find to find one that we don't have a formula for. That's one way. And then I think it's important that you kind of write out your thinking process so that you can just go through the problem, find out different dimensions that you need to complete the problems. Okay, long video tonight. Sorry about that, but thanks for watching. I hope this helps.